on quantum magnonics. So it will be given by Professor Vasil, who came to us from Oakland University, Rochester, the USA. He is here at the Faculty of Physics, University of Vienna, for 2 months as a guest professor. And that's why we have such a great pleasure to learn about quantum magnonics from him. So Vasil is a theorist in the field of spin wave physics, nonlinear physics. He contributed a lot to spin transit torque, to wave turbulence, and now he is interested in quantum magnonics, hybrid systems, classical and quantum, in neuromorphic computing, and very, very broad scope of topics, also many things we are studying here in our group, so it's also a good opportunity for us to talk about research while we are here. Vasil was graduated in Kiev Tarashchenko University. Then he did a postdoc in Weizmann Institute, and then he joined Rochester, where he worked together with Andrei Slavin for many years. Vasil is associated professor there. And also it's very, in some sense, Vasil is a special guest for me. You know that sometimes PhD supervisors, professors are a little bit busy. There is, in some groups, there is such a person whom we name usually everyday supervisor or direct supervisor. And Vasil was my direct supervisor, so he actually tuned to a large extent the all future evolution of my own career. So Vasil, thank you very much that you are here and that you will share with us this fantastic lecture.
Thank you, Andrei. It is my great pleasure and honor to visit Vienna and give this lecture. And it's especially significant that we are here in Vienna talking about second quantum revolution and quantum effects, because in Vienna, one of the great physicists of 20th century, Wolfgang Pauli, was born. And in particular, he, like exactly 100 years ago, wrote 3 matrices, which we know as Pauli matrices. And these matrices describe observable properties of electron spin, spin 1/2 particle. And then were absolutely indispensable in explaining electron property and developing first quantum revolution. But now, more and more people, more and more students, even not from physics, from computing, from engineering, learn about these matrices under different names and different meanings. So they know this as quantum gates, not as observables, not as something that describes property of a spin, but as some actions that we can do to a spin. What's a button that we can press to change its properties. And this change of meaning of the same thing from observable to actionable atom, it's clearly demonstrate our changing understanding and changing approach to quantum physics, which is now called second quantum revolution. And today I will be talking a little bit about second quantum revolution and how magnonics fits into this rapidly developing and exciting area. So first I will give you a little bit like overview of second quantum revolution. What is the spirit of this revolution? Then I will be talking a little bit about classical magnonics. So this is a field that we know very well, that we studied for many years, and I will talk about some unique properties of magnons. What makes them different from anything else that we encounter in everyday life. And finally, I will talk a little bit about quantum magnonics, about emerging field of quantum magnonics, what we can do there, what possibilities exist because of using unique properties of magnons that we know from classical physics, using toolkit developed in the second quantum revolution. So let's start with the second quantum revolution. And here you can see two photos taken 100 years apart. So the first photo, this is a photo of original apparatus of Stern and Gerlach. So Stern-Gerlach experiment was very simple. They took ray of neutral silver atoms and passed this ray through a homogeneous magnetic field. And why inhomogeneous magnetic field? Because neutral silver atoms, they have unpaired electron, which it has magnetic moment. So this atom has magnetic moment. And when magnetic moment moves in inhomogeneous magnetic field, it shifts up or down depending, or left, right, depending on the direction of the spin. And what they saw two spots. Not a continuous distribution, but only two spots. And this is the first demonstration that electron spin has only two possible states, spin up and spin down. Experimental demonstration of discrete nature of electron spin. So this experiment proves that electron is a two-level system. 100 years from this experiment, this is a photo of several years ago, IBM presenting a new quantum computer. So inside of quantum computer, the heart of quantum computer are qubits. And what is qubit? Qubit is just another name for a two-level system. Qubit is any system that has two states. For example, electron spin can be used as a qubit. But we are not just observing these states. We use these states in a computer, and what computer does, it processes information. So these states are used to encode information, we can say that. Spin up is not just spin up, it's our logical zero. Spin down is not just a particular direction, it carries information, it's a logical one. So here we see this change in approach. So what we did during first quantum revolution and during second quantum revolution. So in the first quantum revolution, from 100 years ago to 90s, 60s, when laser was created, we studied natural phenomena. We studied behavior of large ensembles of particles, like an array of silver atoms. There are many atoms, and we studied what is the average characteristics. So we were learning laws of quantum physics, observing behavior of natural ensembles of large number of particles. During the second quantum revolution, which started now, well, no one knows when it exactly started, but it's ongoing, we have a different approach. We are interested in quantum behavior of individual artificially created system, artificially created so they have properties that we want them to have. We are not learning laws of physics. We are not observing nature. We are using laws of quantum world to engineer particular behavior in artificial system. To use this quantum system for information processing, sensing, and so on. So this change between observer attitude to engineer attitude can be further demonstrated using three main quirks of quantum world that you probably heard of: superposition, entanglement, and particular properties of quantum measurements. So for an observer, like how I was taught quantum physics 30 years ago, these were facts to be dealt with. That's how the world works. We have to live with it, and that's all. But if you have this mindset of the second quantum revolution, you are not just dealing with them. You see these particular properties of quantum system as a resource to be used. So let's consider it a little bit more detail. So for superposition, we are saying that electron has two possible states: spin up and spin down. So spin up and spin down. What about spin right or spin left? Are they different directions? Well, so the reality is that these are just two basis states. Two basis states of a spin, but we can also form various superposition of the states. We can combine them together. This property of superposition is one of defining properties of quantum systems. So we can take some part of spin up, and we can take some part of spin down. And there is a difference in their relative amplitude, and we can also introduce phase difference between these two components, because quantum world works with complex numbers. So when we have complex numbers, we have phase difference between two numbers, not just the amplitudes. And when we write general state of electron in such form, we can write it through two angle theta that changes from 0 to pi, and angle phi that changes from 0 to 2 pi. And these are exactly the angles that exist on a sphere in spherical coordinate. So we can describe this general state of a qubit as a position on a sphere, and such sphere is called Bloch sphere. It's not just mathematical fact. If we have many electron spins, like many electrons prepared in a particular state, in a particular quantum state, and then we take this ensemble and measure average direction of its spin or average direction of its magnetic moment, that's the direction that we will get. So when you are dealing with magnetic materials, magnetization is just the magnetic moment of electron spin. It has the same opposite direction, because electron has negative charge, opposite direction to the spin. So when you measure direction of magnetization of ferromagnetic measure, you're actually defining this direction on a Bloch sphere. So this were known during first quantum revolution, and we observed many phenomena and interpreted it like that. During second quantum revolution, this superposition stopped being just a fact. It's a valuable resource. The fact that electron spin can be not just in the 0 or 1 state, so these are just 2 points on a Bloch sphere, but it can be in absolutely any point, is the resource in quantum technologies. We are actively using superposition. We put qubits, two-level system, in a superposition, and then we do some quantum calculations. And superposition is when qubit is both 0 and 1. And this is basis for quantum parallelism. And this is most clearly seen in one of the most important gates in quantum computing, so-called Gadamer gate. So this Gadamer gate, it was not that it did not exist before, but before second quantum revolutions, these matrices were the main matrices that describe that you use when you work with electron spin or two-level system. But these matrices do not create superposition of states. If your electron was stayed up, it will either stay up or it will completely switch. It will not go into superposition state. So these are characteristic matrices or characteristic gates of the first quantum revolution. The second quantum revolution, the most commonly used quantum gate is Gadamer gate. This is the gate that takes spin qubit from state 0 and put it in superposition state, equal superposition of 0 and 1 along the equator of the Bloch sphere. So superposition is a valuable resource in the second quantum revolution. Another property of quantum world is the entanglement. So interesting thing about quantum world is that we make it very different from classical world. If classical, I have two particles, one has some position velocity, other has some position velocity. They may be correlated. For example, if they collide, and I don't know details of collision, that after the collision, I may not know their positions and velocity, but they will be correlated through law of conservation of energy and momentum. But still, I do not know their position, but this position exists. So in such cases, to describe such classical correlations, we use statistical approaches, statistical mechanics, probability distribution. So in classical world, this statistics is needed only to compensate for our ignorance. We don't know position and velocity, but they exist. In quantum world, it's different. If we have two objects, like if we have one electron spin, it can be described by wave function, this position on a Bloch sphere. But if we have two of them, I cannot always assign position on a Bloch sphere to this and position on a Bloch sphere to that. They are described by one wave function. Okay, this is very particular feature of quantum worlds. All universe, strictly speaking, is described by one wave function. And when we consider two electron spins, what are the basis states? The basis states say two electrons both can be up. One can be up, other can be down, or vice versa, or both can be down. But these are basis states. As usually, if we have basis states in quantum physics, we can always form superposition of the states. So we can mix these states as we want. And for example, we can mix them in state which is one of Bell states, one of Bell pairs. So this is state in which one electron, one spin up, other down, or first down and second up. But these two possibilities exist at the same time. They exist at the same time, not like in classical physics. We have one or another, but we don't know which. They exist at the same time. So this is so-called entangled state. And during first revolution, entanglement was one of the most controversial points in quantum physics. It led to very famous discussion between Einstein and Max Born that lasted for like 20 years about what is the meaning of the state, whether they are real or not. And if you want to learn more about such state and whether they are real or not and in which sense, come to my second open lecture at the end of March. So it led to such things like a YPR, Einstein-Podolsky-Rosen paradox, that when these big scientists argued that quantum mechanics cannot be right because it leads to some weird unphysical results. Einstein calls this some consequences of entanglement as spooky action at a distance. And you probably heard about Schrödinger's cat, which is both dead and alive at the same time, which is also entangled state. So this was a source of lengthy debates during first quantum revolution. But in the second quantum revolution, if you have an engineering approach, you see, okay, we have this property, this will be our resource. And in fact, entanglement is the most valuable resource in quantum computing, quantum sensing, and everything. So because like a lot of things, a lot of unusual things that we can do in quantum physics, such as quantum teleportation, quantum communication, this quantum algorithm, which are very fast, they all use entanglement. None of them would be possible without entanglement. Okay, the third quirk in quantum physics is the measurement. So measurement, you probably learned, well, at least when I was taught quantum physics, professor told me that quantum world, like it's in classical world, we can have exact position, direction, but quantum world is all random. We don't know anything. There is no definite state. There are a lot of randomness in quantum world. Reality is no. Quantum world, there is no randomness in quantum world. And this change from random, quantum world random to quantum world is not random, is again one of characteristic of second quantum revolution. And it tells us, professors, that we need to change the way we teach quantum physics. Because if we stay in quantum world, we have Schrödinger equation. If you know wave function in a given moment of time, you will know exactly the wave function in any following moment of time. There is no randomness. Randomness appears when we measure quantum system. That's the only place when randomness appears in quantum physics. And it is described by Born rule. So if we have electron in a particular direction, say it has spin up, but we want to measure what is its projection on x-axis, whether it's plus or minus. Here we will get randomness. Only when we perform measurement of quantum system. Oops. Okay. So during first quantum revolution, this randomness, well, defined our mindset of what we can do. Like if we measure quantum systems, the result is random. So there is no sense of talking about results of individual measurement. Like if you flip a coin and, well, there is tails. So what? It's just one measurement. You need to flip it 100 times and then look at the average quantities. Then you can make some decision whether this coin is fair or not and so on. So that's the mindset of first quantum revolution. Measurement, outcome of particular measurement is random. So we need to make millions of measurements and only statistical averages have sense. And this is the formula for expected value of operator. This is like the most important formula during first quantum revolution because it was the only thing that we measure. Average quantities of different observables. Second quantum revolution, we have different approach. Okay, result of individual measurement is random, but this result tells us something about state of the quantum system. And there are many quantum technique appeared that use this information. For example, we can use this results of measurement and this randomness in measurements to correct for errors in qubits. So quantum error correction algorithms, they use this measurement. We have a qubit in some state and there may be some error because there is noise and stuff like this. We can measure it, well, we can partially measure it, I would call it like that. And then depending on the result, we can apply one of the gates to correct it, to correct the errors that exist there. Quantum teleportation would not be possible without this randomness in measurement. There are other techniques like we can use these random measurements to create some states with some particular properties. So for example, we can create several, say, photons and then put them through a system of beam splitters. And the output result will be random. It will not be random. There will be many different possibilities of what will be the output result. But we can measure part of the output beams. And say we measure that, okay, there is 1 photon here and 0 photon there. This information tells us what is the state of the remaining photons. And we can choose in our subsequent actions, we can choose only those cases that produce states that we want. So this is so-called Heralding technique or conditional quantum programming. So again, this measurement became a valuable resource in second quantum revolution. So as a flagship of the second quantum revolution, here we have quantum computers. So quantum computers exist with more than 100 qubits. You can build quantum program yourself and run it. This is the result of execution of a program. This particular program realizes, of course, super dense coding. One of the quantum possibilities, how to send 2 bits of information using just 1 quantum bit. And this is the result of measurement on an actual quantum computer prepared specifically for this lecture. Okay, so quantum computers are quite well developed. So there are two characteristics that have we specify whether they are powerful or not. The one is so-called quantum supremacy, which was crossed by Google 7 years ago. Some people argue that it was not real quantum supremacy, but generally, like, we agree that, yeah, this is. So what is quantum supremacy? Quantum supremacy is when quantum computer can solve any problem, no matter how useful this problem is, can solve any one particular problem which cannot be solved using classical computers. So, but, well, to show quantum supremacy, you specifically design a problem which is very good for quantum computers and very bad for classical one. But we cross this threshold. Much more useful is so-called quantum advantage. So quantum advantage is the point when quantum computers can solve at least one practical problem faster than any existing classical supercomputer. So we're still not there yet. So quantum computers are not practically useful, but they can be used for research, and it's really fun to play with them. They can be, and they develop very fast. Okay, so beyond quantum computers, second quantum revolution proposes some important advantages in communication. For example, quantum communication based on quantum key distributions. They promise communication which will be secure at the level of physical laws. So communications that cannot be broken, like physical laws prohibits anyone like eavesdropping on communication. Quantum sensing, using quantum states and non-classical states of quantum systems, we can improve accuracy and sensitivity of measurements. This can be used for gravitational wave detectors, navigation, medical imaging, and a lot of things. And in general, so this is typical list of application of quantum technologies that will be useful. But, well, I don't think that inventors of internet would have guessed that we will use them to post our photos on Instagram or even buy stuff on Amazon. It was like, whoa, we will use internet for exchange of quantum information, scientific information, things like that, yeah. But it is used for that, but there are much wider range of applications. So this quantum technology, when they will be developed, they will have much wider applications that we simply cannot imagine now. So this transition to second quantum revolution was recognized by two recent Nobel Prizes in physics. So 4 years ago, there was prize for experimental demonstration of Bell inequalities, and one of professors in Vienna, Anton Zeilinger, also was a recipient of this. And last year, the Nobel Prize in physics was basically for discovery of superconducting qubit. So this qubit, which is a transistor of the second quantum revolution. Okay, so, but of course, not everything is without problems. So there are many problems right now, or which we can anticipate, for which, well, some solutions are needed. So there are many of them. I chose like three particular. For example, there is speed lifetime bottleneck. There are many designs of qubit, of these quantum zeros and ones. We can design them in different ways. And there are designs which are very fast, so we can do operation with them very fast, but they do not live for a long time. So in a matter of microseconds, they experience decoherence, information is lost. From the other hand, there are qubits like nuclear spins that live for a very long time, but it's very difficult to perform operation on them. And these two properties are related to each other. Because what does it mean that we perform operation on qubits? That means that qubit interacts with environment. What means that qubit experiences decoherence? That means that qubit interacts with environment. So the faster operations on a qubit we can do, the faster qubit will decohere. So this is like a principal thing, and so far there is no good solution. One promising approach is to use hybrid architectures. This is what we have in our everyday devices. So hybrid architecture is when we are using different types of qubits for different purposes. We will have fast qubits for fast information processing, and we will have slow but long-lived qubit for storage, like RAM or ROM, or for storage of quantum information. This is a very nice approach, but what we need, like this fast and slow qubits, they do not talk to each other directly. You cannot transfer information from memory to processor. It's not that easy. We need some mediators that will take this task. Second big problem is the quantum internet. Quantum processors, like the one that IBM produces, for example, they have qubit. So we have two-level system, two energy levels, and there is some correct frequency of transition. So for superconducting qubits, this frequency is 5 gigahertz. But suppose we want to send this information to another computer, so we want to develop quantum internet. Well, without quantum internet, quantum computers will not be very useful for everyday tasks. So we need to send this quantum information over environment at 300 Kelvin. So we cannot use this information at 5 gigahertz because thermal energy is much higher than energy corresponding to this quantum. It will be destroyed by thermal fluctuation. We have to use optical photons. But optical photons, they have frequency like 100,000 times higher than frequency of qubit. So we need to develop microwave to optical transduction, a way to convert quantum information from 5 gigahertz to 200 terahertz. And we need a physical mechanism for that. Third problem is connectivity of qubits within quantum processor. So here is the actual topology of one of actual quantum processors of IBM. So each dot here represents a qubit. There are more than 100 qubits. Okay, so this is actual processor. If you take my course on quantum computing, you probably will be running labs on this processor. So each dot is a qubit. Each line means that we can perform some operation on these two qubits. If two qubits are not connected, directly connected by a line, you cannot do operation like AND or OR on these two qubits. You need first to, so if you want this qubit and this to interact, you need first to bring information from this qubit along this path here, and only then you can do it. So, of course, this is very bad. So connectivity is, it's not like you can take qubit from here, qubit from there, make some operation on them, and then put them back in their respective places. So connectivity is very bad. And if we scale this computer, this problem will become worse and worse. So what we can do here, we can create some kind of quantum bus, the same bus as exists in the classical processor. So some quantum bus that will take quantum information from each qubit and can transfer it to a different place. Why it cannot be done just with electromagnetic waves? Because we have frequency 5 gigahertz. Wavelengths of electromagnetic waves of this range of near field is several centimeters, is larger than this dimension. So using electromagnetic waves, we cannot address individual qubits. We need waves at 5 gigahertz, which has wavelengths like micron. And then we can address individual qubits in such topologies. Okay, so this is a brief overview of second quantum revolution. Now the question is how Magnonics fits there. And first, before considering quantum Magnonics, we'll consider a little bit of classical Magnonics if you don't know what classical Magnons is. It's very simple introduction. So spin waves or magnons, these are collective excitation of a magnetically ordered medium. What does it mean? So this is like a picture of ferromagnetic materials. Ferromagnetic materials means that the atoms there, they have spins, and these spins interact with each other, and they want all to point in the same direction. And this direction usually is defined by some external field. So you have here a field, and all spins point in the same direction. It's not that easy to change direction of spin because there is very strong exchange interaction. This is what makes ferromagnetic material different from other type of materials. What happens if we somehow deviate these spins from their equilibrium direction? This is what happens. The spins will precess, so each spin will precess in a conical fashion about this equilibrium direction. This is called precession, and this precessional dynamics is the same as with children's toy top. You know that when you spin some top like this and then push it, it starts to precess like that, or something that you can see in gyroscopes. Okay, so this picture shows a case when all spins precess with the same phase. So they have the same phase, so if we consider it as a wave, this is the wave with infinite wavelengths, or zero wave vector, because wave vector is inverse to wavelengths. We can also create spin waves with non-zero wave vector of finite wavelengths. So here we have wave that like there is phase difference between these spins, and this represents propagating waves. If you just look at this, you see, if you follow like this direction of spin, you see that it propagates from left to right. So these are propagating spin waves that can carry information in space from one space to another. And here is just a cool illustration of two-dimensional spin waves. And if you look at this picture, you see that there is waves that goes in that direction. Okay, so this is what spin waves are. Basically, we have these spins that precess, that's all. We have this oscillatory and wave-like behavior. So what makes them different? Well, so first, here is a mathematical description. To understand deeply what makes this very special, you of course need to go into math. We will not be going there very deep. So, but main unique properties of spin waves can be considered understood just considering these two equations. So this is the equation for magnetization. This is the equation that describes precession of individual spin along direction of effective magnetic field. So, and this is the expression for this effective field in ferromagnetic material. If we consider just a single spin, so this is something that you considered probably during introductory physics classes. So we have spin or magnetic moment, it doesn't matter, in a magnetic field. So it will precess like this, but in the effective magnetic field, we will have only external field because it's isolated spin. There is no interaction of spin with itself. In ferromagnetic materials, we have plenty of spins which are arranged in a particular order. So they can interact with each other. And because of this interaction, we do not have just external magnetic field here. There is interaction through exchange. So that's the interaction that keeps the spins together. There is dipolar interaction because we are talking about magnetic materials. So they create magnetic field. And they can interact, and there is interaction like interaction of usual magnets, attractive, repulsive. There is anisotropy, which is interaction, magnetocrystalline anisotropy, which is basically interaction of magnetic system with crystallographic axis. There is such interaction because spins that we are talking about are not just free spins. They are spins of atoms that sits in crystallographic lattice. So the spin and lattice, they interact with each other. So just keeping in mind form of this equation, the fact that we have many terms here allows you to understand many important properties of spin waves, such as, for example, time reversal, broken time reversal symmetry. If we have spin and it spins, it always spins in one direction like this. You cannot make spin to precess in opposite direction. The same happens with mechanical gyroscope or top. So if you spin it with particular direction of spin, like this. It will always precess in a particular direction. Because here we have this particular direction of spinning, and here this spinning direction is spin, intrinsic property of electron. You can understand that there is a particular direction of spinning, that it can spin in opposite direction just by looking at this equation. So here we have this, the rate, the velocity of this end of this vector is determined by this cross product of effective field and magnetization. So cross product, you can use right-hand rule and you can find what is the direction in which it will go. And there is only one particular direction, so called right-handed precession. So if you have a movie of spinning magnetic moment or spinning electron or precessing magnetic moment, if you run this movie in reverse order, you can say that something won't happen, because if from this picture, if you run it in time reversal order, you will have left-handed precession, and spins cannot precess left-handedly. So this asymmetry between how this process looks like like forward in time direction and backward in time direction. This is what describes breaking of time reversal symmetry. We will not be using it a lot during this lecture. Well, I think not at all, but this is very deep property that allows to create devices which are not possible to create using, say, mechanical waves, in which, like mechanical wave, if you have oscillation like this, you can have oscillation like that. So, like, I don't know. If you have mechanical pendulum, so imagine that you take movie of that and then you run into backward order, it will look exactly the same. And if we use in conical motion, it can move like this and it can move like that. This is unbroken time reversal symmetry. And there are limitations of what you can do with system like that, and magnetic system allows you to do more. There is another important thing, is that magnetic materials are characterized by very strong nonlinearity. So, and you can understand that from the form of this equation. So here we have, this is the velocity vector, dm by dt. So this is velocity vector, and here we have cross product. So cross product, direction of cross product is perpendicular to direction of each vector. So what's important is that this cross product is orthogonal to direction of magnetization. So you can, using mechanical analogies, this would be the position and this would be velocity. So you have velocity which is orthogonal to your position. How would you move in such case? It's a circular motion. Velocity orthogonal to position. Or in three-dimensional case, you would move on a surface of a sphere. So this is how spins move. They must move on a surface of a sphere because of this rule. Physical reason behind this behavior is very strong exchange interaction. That all spins are kept together, so they must move like that. What that means? Like, sphere is not a flat surface. And this curvature of this phase space of magnetization translates into nonlinearity of oscillations. So here is some depiction of precession. What happens if we increase amplitude of this precession? And you can get, well, under certain conditions, you can get very weird trajectories. They exist because this magnetization vector, it must move to on a sphere. So spin waves, they are characterized by extremely strong nonlinearity that does not require any nonlinear interaction. Like, there is no nonlinearity in this term. Nonlinearity sits in phase space. So we don't need to invent nonlinear interaction for spin waves. Nonlinear interactions are always present because we have this nonlinear sphere. Okay. So some more properties of spin waves. So first of all, Well, this effective field that determines how fast magnetization moves. It has external fields, so this is the field that you apply. So that means that the frequency of this precessional motion will depend on external fields. So we have tunability of frequency with magnetic field. So this is very useful property. We can have an object that has this resonant precession frequency 4 gigahertz, and then we can change it to 5 gigahertz for 10 nanoseconds simply by changing magnetic field. So that's the tunability with magnetic fields. So here I show the graph of dependence of frequency of this uniform k equals 0 magnons on magnetic field. And this and here these 3 lines correspond to 3 different geometries in which we perform or excite such uniform precession. And this graph also illustrates another important property of spin waves. That there are frequencies and all other properties that depend on direction of magnetic field and shape of magnetic element we are using. And the reason for that is that here we have the dipolar interaction. And if you ever played with magnets, if you have 2 magnets, and you put them like this, they want to point, like this is north pole and this is south pole. They want to point like that, north to south. But if you turn them in direction like this, they will flip like that. So this dipolar interaction, whatever, it depends on spatial arrangement of magnetic elements. So whether we have sphere or plane, and depending on how we magnetize it, will result in different properties of waves that exist and different frequencies of this. This is also very important because we know how to use this property. We can engineer, we can create magnetic element that will have definite certain frequencies that we want. We can engineer a spectrum of spin waves in magnetic nanostructures using combination of this factor. One more important property of these spin waves is shown here. So here I show the spectrum of propagating waves, so waves that has non-zero wave vector or some finite wavelengths. Again, for Yick field magnetized like this. So this is how this dispersion looks like. This is the same dispersion, but a different range of wave vectors. So here from 0 to 5 inverse micrometers, and here it's much wider range, up to 50. So in this region, this shape of dispersion mostly governed by dipolar interaction, and in this region mostly by exchange interaction. What is important is this scale. So the frequency is like 5 gigahertz. That's the frequency of superconducting qubits. So this wavelength here, this point corresponds to wavelengths of 10 micron. Here, this point corresponds to 1 micron. Somewhere here we have 100 nanometers. So for comparison, wavelengths of electromagnetic wave would be several centimeters for this frequency. So these are waves that have extremely small wavelengths. Therefore, they are very well suited for different miniaturization, for nanotechnology, for spin wave processing in a nano world. Okay, and these are not all the properties. Like if we change direction of magnetic field, we can have very weird waves that has like backward direction of dispersion. So this is frequency decreases with wave vector. It's very interesting. It can be used for many different purposes. Or we may have surface waves which are localized near surface of the field. And we know all these properties from classical magnonics. So one more important property of spin waves or magnons is that they can be coupled to many different excitations. So see here again, in this expression, here we have external field. Microwave field. And it does matter whether this is constant field created by magnet or this is magnetic field created by photons that flies nearby. And what that means? That, well, since we have here this external field, that means that spin waves can directly talk to microwave photons. Or they can directly talk to anything that creates magnetic field. For example, current in a circuit. If we have a circuit, there is flowing current, it creates magnetic field. So this circuit with current can talk to spin waves. This is actually how we create them, how we generate spin waves in classical applications. Here we have anisotropy. What is anisotropy? It's the interaction between magnetic subsystem and crystallographic lattice. And that means that spin waves can talk to excitations of lattice, which is sound waves, phonons, mechanical vibrations. Spin waves can also interact with optical photons through magneto-optical effects, such as Faraday rotation, something probably you did some labs previously on Faraday rotation or brilliant light scattering, one of the main techniques to study spin waves. Okay, so spin waves have a number of unique properties that makes them very different from usual waves. And the origin of these properties can be easily understood just from these two equations. So now the question, how we can utilize these properties in quantum realm. So let us move to quantum magnonics, and the first question we would like to answer is, what is a magnon? What is a single magnon? So here I have this picture of uniform precession. I can calculate like what is the energy of this precession. So I can say, okay, an energy of this precession will depend on precession angle. The larger precession angle, the larger the energy. Smaller the precession angle, smaller the energy. So I say like, okay, let's decrease this precession angle down to smallest possible value. So we would probably achieve like single photon in that case. So let's do this and let's see what we will have. So suppose like this angle corresponds to energy of precession equal Planck constant times frequency, h omega. So this corresponds to 1 quantum, hopefully. So if you look at individual magnons at a particular moment of time, what you see? You see direction of magnons at a particular, the direction of spin, which is not vertical, which is not down, but at some tilt. So we can use this block sphere representation. Okay, so this is direction up, this is direction up, down. So this tilted direction is a superposition of up and down. Okay, we have very small precession angles. So this cosine is 0, this sine is very small, I will denote it epsilon. So when we look at one spin, we can write it like this. It's almost completely up with small direction down. And now we have many of these spins. So let's strive to write wave function of a single magnon. So we have tilted spin 1, tilted spin 2, tilted spin 3, and so on, tilted spin 10 to the power of 20. Each of tilted spins is like that. So the question, does this wave function represent a single magnon? And this is very an obvious question, and the answer is no. Why it's no? Because here, when we have this precession picture, at a particular moment, we have a definite phase of precession. Phase and number of particles are conjugated variables in Heisenberg uncertainty relation. Of course, you know uncertainty relation delta x, delta p is greater than h bar. This is the usual. Position and momentum are conjugated variables. But as well, phase and number of particles are conjugated variables. So if we have definite number, if we have definite phase, that means that number of particles would be indefinite. Let's see how this. So to see this, what we need to do we simply have to take this expression. So here I have the tensor product, but this works simply as matrix multiplication. We can open these parentheses, we just need to keep order of terms the same. And I can open all these parentheses, I will have very many terms. For example, I will have term like this. This is if I take spin up, spin up, spin up, and so on. So what this term describes? This term, like here in this term, all spins are up. So this is like a term without any magnons. So there are 0 magnons. This is ground state. I will also have term like if I take here spin down and all others spin up. I will have term with 1 flipped spin, or I can choose second spin, flip, third, and so on. So these terms, they have only one spin flipped. I will have terms like spin down, and then everything spin up. So these are terms with 2 spins flip, and so on. So we see when we build this naive formula for single Magnon state, we do not get single Magnon state. We have something that has 0 Magnon, 1 Magnon, and so on. Mathematically, you can put exact mathematics to that, and mathematically, this state is described, it will be so-called coherent state. This is the quantum state which is most closely resemble usual classical state. That does not have any interest in quantum properties like entanglement. And we started with classical precession, so of course we get this state. In a single Magnon state, so when we have only 1 Magnon and nothing else, we need to keep only these terms, only terms with 1 flip spin. And this state like this, you cannot, in state like this, you cannot say what is the state of each spin without specifying what states of other spins. So you cannot write it as a product. So this is the direction of the first spin, this is the direction of the third, and so on. So this is entangled state. And this is entangled state. How many terms are in this entanglement? As many as we have atoms. So we have 10 to the power of 20 atoms in a magnetic sphere. So we will have superposition entangled state of 10 to the power of 20 atoms. So this is single Magnon state. That is one of the reasons why magnons are so interesting in quantum physics. Okay, similarly so this formula describes 1 Magnon with 0 wave vector. So we can describe 1 Magnon as a particular value of a vector. For this, we need simply to introduce phase shift between these components. Or we can describe 2 vectors of 2 Magnons. So 2 Magnons, they will have all terms with all pairs flipped. And here, there is one like quantum manifestation of strong nonlinearity of Magnons. Each spin can be either up or down, so we cannot flip spin twice. So in this approach, we flip every spin once, and then we flip another spin. There won't be diagonal terms. Terms in which, say, I flip spin 1, and then I flip this spin again. So diagonal terms are absent. This is quantum manifestation of strong Magnon nonlinearity. So this strong Magnon nonlinearity, again, it is built in the form of state of spins. We don't need any particular nonlinear interactions to have nonlinear behavior. Okay, so now let's consider briefly, like, we have this single Magnon state. What can we do? How we can utilize this Magnon state for some fundamental studies? And there are several very interesting proposals. For example, Magnons are very well suited to study macroscopic quantum phenomena. So if we create one Magnon, if we have something like a micro disk of Higgs, so some disk with say size of 100 micron or maybe even up to millimeter, and we excite one Magnon there. And we can do this because we can engineer a spectrum of Magnon in such a way that frequency of uniform precession will be separated from all other states. So we can excite exactly one magnon and say exactly in uniform state. So all these spins in this macroscopic size disk will be entangled. And then we can use this disk, for example, to study diffraction of light on a single magnon. So because we have macroscopic element with a single non-classical quantum state. Or we can use this macroscopic disk to entangle qubits which are separated by distances like millimeter. We can study how fast this entanglement appears and so on. Another possibility of what we can do, we can study this transition between quantum and classical world. So this is one of the problems in modern quantum physics. So what happens during measurement? So when we have quantum system involving by itself, it does not have any randomness in this. Randomness appears when we measure it. But how does that happen? Measurement is a physical process. It should be described by the same Schrödinger equation. So there is something that we don't understand that when we go from quantum physics to classical world. And magnons are well suited for that because even one magnon represents a macroscopic quantum object. And we can very fast, we know ways how we can create like large number of magnons there. So we can probe this boundary. We can increase number of magnons in a disk and see at which point properties of this state change from quantum to classical. So basically answers this question, how many magnons made a spin wave? After what number of magnons we lose quantum properties and we obtain classical object. We can use magnons also to study very important question of nonlinear quantum dynamics or thermodynamics. To study these properties, we need objects that with very particles with very strong nonlinearity. Like nonlinearity in language of particles corresponds to collisions of particles. So collisions of particles, like in wave language, it leads to nonlinearity. Okay, and if we want to study nonlinear dynamics, we need these collisions to happen very fast, faster than natural processes of decoherence. And magnons are very nonlinear objects because nonlinearity is built in their own structure. We don't need nonlinear interactions. We have sphere which is nonlinear by itself. So this nonlinear processes, nonlinear dynamics or thermodynamics may happen on a time scale faster than the decoherence. These experiments actually were done like at room temperature and led to observation of Bose-Einstein condensation of magnons at room temperature. And in particular, they were done here by Andrei Chumak. So we can move it further, we can repeat it like starting from a single magnon and so on. So the possibilities are very interesting. Okay, but can this magnon state be used for something practical? And indeed they can. For example, magnons, one of the property of magnons is that they interact with all types of excitation, with microwave photons because we have magnetic field, with phonons because we have magneto-crystalline interaction, with light because we have magneto-optical interaction. So we can use magnons as universal mediators in hybrid quantum architecture. So we can use this for magnetic elements in which we excite magnon, and this element can connect with superconducting qubits very efficiently with, say, nitrogen vacancy centers against through dipolar interaction, with spin qubits through exchange interaction. So all the superconducting qubit, nitrogen vacancy center, semiconductor spins, isolated spins, not magnons, or phononic resonators. They are all propose quantum systems, quantum qubits with their own good, like unique properties. But these all types of qubits, they do not talk to each other directly. But if we put magnon in the middle, magnon will translate their language from one to another. We can use magnons for microwave to optical transduction. How that is done? Like Well, if we have one magnon and we shine light on it, so there is a process there's a process which is the same as process happening in magneto-optical modulators, but happening on a single magnon level. So this incoming pump photon may absorb magnon, and as a result of this absorption, its frequency will change, will increase. This is called anti-Stokes scattering, which is routinely used in classical magnonics to visualize Magnon states and visualize Magnon dynamics. We just need to do it with single Magnon. So pump photon, which does not carry any information, it's just there, while interacting, absorbs magnons that carry quantum information, will result in a photon with different frequency, and different frequency means we can filter it out from this pump beam. So with different frequencies, it will carry the same information as this magnon. So, and this process is reversible. We can run it in opposite direction using Stokes scattering. Finally, we can use the property that magnons have very small wavelengths, micrometers or below, and we can use magnons for developing of quantum bus. So here, we have this nano-waveguide of ferromagnetic material in which we have this very short wave propagating magnons, and this waveguide is connected to many, hundreds of qubits. By tuning magnetic field, with special tuning of magnetic field, we can put particular qubit in resonance with this waveguide. So we can controllably transfer information from qubit to waveguide, then it propagates along waveguide, and when it reaches target qubit, we can tune frequency at this point, and magnon will jump, will exchange with the state of the target qubit. So this is like magnon, quantum bus mediated by magnons. Okay, and so here is like dream, a vision of what we can do with magnons. So here we have magnon-mediated quantum processor. So we have arrays of superconducting qubits, which are small but connected, so they can do some simple operations very fast. And different arrays are connected by our magnonic highways. So this waveguides that take quantum information from this place and transfer it to some other place. And this quantum processor has dedicated quantum memory that features different type of qubits. For example, qubits based on nitrogen vacancy centers, which are very long-lived, but they don't want to talk to anything except magnons. So this conversion between this quantum RAM and our usual superconducting transport qubit again is achieved by magnonic mediators. And finally, this quantum processor will have quantum internet port, where we will have these X spheres and we will have lasers shining on them, and laser will convert quantum information from microwave range to optical range. So this is like a big dream of people working in quantum magnonics. So how far are we from this dream? Well, quite far, to be honest. So there are many problems, many technical problems that will be solved. They are being solved, but there are like many of them. Some of them are not so big problem anymore, but others are still waiting some good decision. So currently there are only a few first experimental work in quantum magnonics. So this field which like started to develop intensively only recently. So there are just a few works, like here I give like in 2 slides, I give overview of all important works, experimental works in quantum magnonics. There is demonstration of magnon qubit vacuum Rabi splitting. So here in this experiment we have qubit, and we have a ferromagnetic sphere, so basically magnon here. And this splitting, this anti-crossing demonstrates that these two objects, they interact, and interaction is coherent. Coherent meaning it keeps quantum information intact. So that this is proof of principle that we can use this coupling of magnons to superconducting qubit. So the same group, this group of Nakamura from Japan, like uses the same setup to observe, to resolve individual states of magnons. So what was done in this experiment is this Higgs sphere actually was excited by a classical source, classical microwave source, with very low power, extremely low power, like femtowatts. But it's classical. And classical means it has definite phase. And as we saw several slides ago, when we have definite phase, we have undefined number of magnons. So when we excite Higgs sphere with such classical source, we have superposition of state with 0 magnon, 1 magnon, 2 magnons, and so on. Well, mostly it is 0 and 1 because we have very low powers. And with but using measurements of qubit, measurement how this state act on qubits, they were able to resolve individual states, to say what is the probability that we have 0 magnon, what is the probability that we have 1 magnon, and so on. This is our recent work by another experimental group from China. And in this work, there was first attempt, successful attempt to create some non-classical state of magnons. So in this experiment, the state of magnons was classical. We resolved individual magnons, but state was classical. So here it was an attempt to create non-classical state, like superposition of 0 or 1 magnon, or Bell state between magnon and qubit. And basically, this like 4 experimental works gives you a comprehensive review of experimental achievement in quantum magnonics. This is a field that only starts now. So, and with this, let me conclude. So, magnons are collective spin excitations that have a lot of unique properties. In quantum magnonics, it has a great potential both for fundamental studies and practical application. And research in this field has just started because only recently we got tools that we can use to do this type of experiment. So quantum magnonics is indeed a new frontier in the second quantum revolution. And if you are a young scientist, that means that it's not too late to get onto this train. Thank you for your attention.
Very much also for this amazing lecture. I myself learned a lot. So let's make it as a scientific talk. Other questions?
Any question?
Maybe I will start. I actually have many, but now I have 2 months. Let's start with the most important, physical magnon. Yeah, we discuss it all the time with many people, and usually we say in the style that it's block magnon, so like slip of one spin, but we don't want to have, because there's exchange interaction, we don't want to have a flip, and we distribute it like you have had it before. Yeah, a small angle, the same change in magnetization. So actually I advanced today because he said that it should be not a one block magnet, it's more or less entanglement of all possible block magnets in the system, which makes it very different. Thank you for this. But how about exchange interaction? So how close is this to reality? Yeah, we cannot really take magnetic material and flip one spin, it will be huge energy problem. So if you have a little angular continent.
No, it will not be huge energy. Like, yes, so here we have like 2 spins, like spin up and spin down. So at this point, exchange energy density will be large. But you take into account that you have capital N, which is number of atoms, terms in this expansion, right? Like you have a material with, like say, X sphere. So how many spins do you have in X sphere?
I used to take volume divided by 124.
Say 10 to 18.
Yeah.
Like this. Well, when we are talking about such large numbers, 1 or 2 orders of magnitude here, that it doesn't matter. So for simplicity, I wrote a state like that. But in reality, of course, state need to be normalized. So here in this superposition, we will have capital N terms, right? Well, this n number of terms, because we can flip any of these n terms. So to write normalized state, we need to put here normalization constant. And then we can do this. Basically, so now when you calculate energy of this state, well, you can calculate energy, it will be divided by this factor squared, right?
So then you want to say that energy will...
So yeah, like we have like large energy density, but it appears like it will appear, say, not in too many terms. Okay. So of course there will be exchange energy associated with the state. But we have magnons have finite frequency. So Magnon spectrum has a gap. So what it means, there is certain minimum energy that we need to apply to flip once or to create one magnon. So of course there will be energy associated with this state. But this energy will be much less, like factor of n less, than exchange energy of flipping, like of taking 2 spins and actually flipping. So if you compare this state, we say this state like this. So this is a Magnon state. It's a superposition of many states. They all have this factor. And you can calculate energy of this state. And you can calculate energy of state like this. So this is not superposition. So there is no factor 1 over square root of n. There is just one term. And in this term, we took and flipped this spin. So energy of this state will be exchange integral. So it will be milli-electron volts. Energy of this state will be much less. It will be like exchange interaction will be divided by this factor n. You need, I'm sorry, I don't know how to explain it without mathematical derivation, but the fact is that you cannot just look at this energy. You have to take into account that in the overall sum, it will have very small contribution. Like you can think of it as, yeah, there is a probability of having this configuration, but it's very small. So it gives contribution to energy, but it's reduced by this factor.
Yes, one question is like about the phase number uncertainty. So suppose when we have defined phase, we have an undefined number of magnons or distribution. But if we excite one magnon, then the phase is uncertain.
Exactly.
But is it the phase between the spins, or is it the phase in total?
This is a good question. It's not a phase between spins, because in state like this, all spins have the same phase, but we don't know what this phase is. It's like superposition of all possible phases. You can think of it like that. This is the same. It's not that easy to understand, but if you remember what was told about a quantum harmonic oscillator, if we have quantum harmonic oscillator in the first excited state, What is the phase of wave function? It's undefined. So if we have quantum harmonic oscillator, so we have parabolic energy potential, we have ground state, we have first excited state, second excited state, and so on. How wave function looks in the ground state? Wave function squared. Like this. How this is like probability. How does this probability changes in time? When we will observe. How this probability distribution changes in time? When we have an oscillator in a ground state. It does not change because this is eigenstate of energy operator. So they are defined like states for which probability stays the same. In the first, so this is n equals 0. In the first excited state, what is the probability distribution? It looks like this. It has peak here, peak there. How does this probability changes in time? It does not change. And this is very different from what we observe. And we can go so up and up and up, second, third, like 100,000. There will be some probability distribution, but it will not change in time. When we are talking about definite phase, we almost always talking about this phase changes. So I have pendulum with phase changes. So here, probability change oscillates in time. How do you get this change in probability from such building blocks that do not change in time? You get it by forming superposition of the states. And what we observe in everyday life is not a state with very large number n. Because state with very large number of n will still have stationary probability distribution. There won't be any motion. What we see as classical oscillation is the superposition of states with different n. I will demonstrate this on my lectures in 1 month. So when we combine these states, then then look at the probability of the superposition. Because of presence of terms that interfere, because we have this interference, we will have probability distributions that moves like this in an oscillatory manner. So moves exactly like classical one. So classical states are superposition of quantum states. This is exactly what we got for sync magnons. We started with state of particular phase. This is classical state. We started with classical picture of processing magnetization. It's classical state. And we get classical state written in quantum notations. Well, not classical, coherent state. Yeah. Yes, please.
So when you talk about application of quantum mechanics, you're always the 3 examples you showed are all at the interface of existing other quantum technologies. What's the reason that you don't talk about quantum mechanics as quantum processing? Is this an inherent problem of the technology, or is it not there, or what's the reason there?
One reason that say it's not the only possible application. So, for example, during this quantum transduction, we can also perform operations. For example, if we have, this is not just the transduction. For example, suppose I have this Magnonic bus, quantum bus, and there is 100 of qubits. I excited quantum bus with 1 qubit. And then I can spread this quantum information across hundreds of others. I will just make operations such that not all quantum information will be exchanged between Magnon and qubit, but say 1/100 of it. As a result, I may get entangled state of 100 of qubits in one operation. So this is one possibility. So there are possibilities of using magnons for processing of quantum information. What magnons are not very good at, they are not very good as qubits themselves or like quantum memory. Why? For the same reason, there is like dichotomy between fast and slow. Magnons talk to everything. Magnons interact with any other excitation. And that means there are many channels of decoherence for magnons. That means their lifetime is not very good. So as a memory, they are bad, or as the qubits themselves. But they are very good at transduction, taking quantum information from one form to another, or processing of quantum information. So both this application can be done with. Well, there are also some exotic applications of magnons, for example, like detection of axions, hypothetical particles that may explain like dark energy and dark matter problems dark matter problem in current cosmology. But this is very important, and there is like a lot of research in this direction. But we don't know whether axion exists or not, and this is not something that you would do every day on your quantum laptop, right?
People propose to use Magnon to detect axion?
Yeah. Because these axions, like these are theoretical particles, there should be interactions that interact directly with spin. So we can use magnons to detect them. Like you have this ferromagnetic sphere cooled down to million microkelvin, so there is no interactions. And if you will detect that their magnon appeared, that means that something created it. And this, like using like different characteristic of this process.
There are some quantum fluctuations people have said.
Well, quantum fluctuations still means we are sitting here. Quantum fluctuations means we have this state, but in this state, if you measure position, you will not have here. You will have spread. So this is quantum fluctuation. But you will not see it as, say, as some energy. So if we have this magnetic sphere connected to qubit, and there is like, we exchange magnon and qubit and measure qubit. Exchange magnon and qubit, measure qubit. And we do not excite qubit. Qubit always stays like in zero state, and magnon in zero state. So what we will get as the reading? 0, 0, 0, 0, 0. And then we get 1. How can we get 1 in this? It means that qubit was created here. It was created by new interaction, because we shielded this X sphere from all interactions that we know. It means that there is new interactions that created this qubit. And then studying characteristics of how these qubits are created in arrays of these X spheres, we may hopefully we will be able to say something about this hypothetical axion particles that create this magnon. So this is the idea, but they still stay hypothetical. There is research there, but no progress so far.
I will ask one probably last question, but very important one, which we discuss with Nakamura and other people at conference. Usually it's asked, if I take X sphere, you said that yes, there is because of a strong exchange interaction, magnetization vector always draw sphere and so on. And now imagine I have the best possible Kittel mode, only one X sphere, as low temperature as possible, and so on, and I excite this small single magnet, or just even many magnets, the large precession angle. How about the coherence? Do we have the coherence there? Or system in ideal case will keep it always?
This is excellent question. This is absolutely excellent question. And one of the things that I was chosen, which three fundamental application to show, that was the first candidate that I eliminated. We don't know. Honest answer will be we don't know. Because we have this entangled state of macroscopic number of spins. How can this state keep its coherence even for 1 microsecond? This is not clear. We have to study this. So, and hopefully, like I think this would be like the first fundamental result in quantum magnonics. We will get some new information about processes of decoherence in solid state. Because I can say, like, theoretically, yeah, there won't be any decoherence if everything is ideal. But I would not bet even $1 on that answer. So this is something that we need to study experimentally. So there should be some limits to this decoherence-free dynamics, even if we eliminated, say, thermal phonons, thermal photons, all other thermal effects. Even if we eliminated defects, crystallographic defects. But this is something, this is a question that you should answer because you're experimentalist. But this is very excellent. This is really the thing that we don't know. I can tell you about theoretical picture. Yeah, it will go forever. But the same happens with a mass spring system without damping. It also should go theoretically forever, but I was never able to achieve this in real life.
Now we just have to realize.
Yeah.
Okay, then I think we are done for today. Thank you very much.
Thank you.